Hi, and welcome to the full OnSSET-specific model introduction, code running, and tailoring video. Here, we will get further into the details of what OnSSET, the open source spatial electrification toolkit, is, what it is used for, how it works, and what kinds of data it needs. We will also cover the specific modifications made to it for its role in the RE4AFAGRi integrated modeling framework, and how to run the OnSSET Python Jupyter Notebooks code on your own computer. We will also briefly cover some tips for data validation, scenario customization, starting a new country analysis, and the best places to get help if you get stuck. Please make sure to watch the other introductory RE4AFAGRi videos to understand the context of the challenge that our integrated modeling platform aims to address. And lastly, we thank the EU Horizon 2020 Research and Innovation Program for the funding received to carry out this work. We together have developed the multi-model integrated RE4AFAGRi modeling platform. Here we integrate 4 different models, including water crop, looking at water needs and constraints across the continent, MLED, which looks at electricity demand for all different sectors, the NEST model, which looks at long-term scenarios and investment requirements, and OnSSET, which is the focus of this talk today, which looks at the specific supply option optimization of individual communities across a country or continent. OnSSET stands for the Open Source Spatial Electrification Toolkit. It's been developed by many different institutions across the world, including reputable organizations such as the World Bank, KTH, United Nations, International Energy Agency, NASA, and many, many others. The geospatial energy access planning problem has many different challenges, however, with also many different opportunities. There are several supply technology options available, including centralized grid extension, mini-grids, and standalone systems. This also needs many different data sources and scenarios such as population, energy resources, infrastructure, demand, and costs. Doing this in a very often data-scarce environment and planning for scenarios of a very uncertain future. Gladly, many new modeling techniques and data have become available, including satellite image processing, machine learning, which have revolutionized possibilities and widespread data availability, and multi-scale modern integrated platforms such as the RE4AFAGRi system presented today using OnSSET and other soft-link models. Many options exist for providing electricity access to communities across the world, but they can generally be categorized into 3 different sections, including centralized grid extension, which also requires the supporting generation capacity and grid extension, standalone systems such as solar home systems, solar lanterns, or diesel generators, and also mini-grids, which include local generation and distribution systems, typically solar, but also hydro, diesel, wind, and hybrid combinations of all 3 of these. These can provide many different energy services across the chain, including sometimes more services where energy-efficient devices are used. So many solutions exist, but which ones are the best? Where should we deploy them? How much will they cost? And when should we do these? For every single community across the world, they have different local contextual situations, including how far away are they from the existing grid network? What resources do they have nearby, including hydro, wind, and solar? How many people live there? What is electricity demand? What kind of activities exist, etc. And the list goes on. This question then also needs to be asked for every single community that does not yet have electricity. OnSSET is a GIS-based optimization tool that supports electrification planning across countries and regions to determine and reach energy access goals. It combines and uses many different geospatial data sets, and at the settlement level can help to determine energy access solutions. It combines energy demand, population distribution, energy resources, proximity to energy and transport infrastructure, and all of the different cost and performance parameters of different energy technologies included, such as those of individual systems, mini-grids, grids, etc. OnSSET is therefore the perfect tool to answer our question posed earlier for which settlements should get which options. Using the geospatial processing and least cost supply modeling, the capabilities of OnSSET, we can answer this question for every settlement in a region or country. So what does this actually look like? Here we can see an example for Zambia, including in the SDG 7 Universal Access by 2030 scenario. Which solutions would be the best for over hundreds of thousands of individual population clusters across Zambia in the year 2030? In the map shown below, we can see this scenario plotted out. In the blue, we have where grid extension is expected to be the least cost option. In yellow, where standalone solar home systems are expected to be the least cost option. And in green, where solar hybrid mini-grids are expected to be the most cost-effective option. OnSSET also provides us much more information than just which options are expected to be the least cost. It explains for each and every population cluster model how much population is expected to be there in each year, the electricity demand from the different sectors, the electrification status, how many new connections might be required, the installed capacity of those connections, investment requirements, as well as the levelized cost of energy expected in each of these locations for each and every option investigated. Now that we understand the basic purpose and outputs of OnSSET, we can get further into the details of how we use it in the RE4AFAGRi modeling framework and the modifications we made to it for this role. We also will get into some of the specifics of the modeling flow and building blocks of OnSSET and which data it needs, both in isolation as well as from the other integrated models such as MLED and NEST. To understand how OnSSET works in the RE4AFAGRi platform, we also need to understand some of the basics of NEST and MLED. Here we will also show some of the integration between these other models, specifically for MLED, including its electricity demand estimations, and NEST for its electricity supply costing on the grid's supply network. In this integrated modeling platform, OnSSET is responsible for determining the specific energy supply options for each and every individual model settlement. However, to understand how much electricity demand is needed at each of these settlements, MLED is used to generate this output. It also allows us to better understand the electricity access rates in these areas and how much demand is to be met into each of the future time steps. OnSSET additionally needs to include all techno-economic and geographic factors, including the cost of supply technologies, the distance to the grid, how much solar resources available in each area, etc. These outputs are then given to NEST, where it is informed of how much demand is needed to be met by the grid in each of those areas, as well as how much is to be met off-grid. This has important implications for national electricity planning, especially the centralized generation and transmission infrastructure needs. OnSSET itself does not include or optimize what specific supply technologies are included on the grid, but it does have the grid as an option. NEST also gives OnSSET how much the grid is expected to cost, which is used to understand how much the electricity should cost in each and every village if grid should be extended to those areas. When combining several different models together, it's important to understand differences in these models, especially their spatial resolutions, time resolutions, and to account for harmonizing these different sources together. OnSSET models every single settlement at a vector scale at the settlement level resolution. This is different to something like NEST, which instead models at the river basin catchment area resolution. Additionally, OnSSET in this scenario only models specific milestone years of the year 2020 as a baseline, the year 2030 as a midterm target, and then the final year of the year 2060. EMLIND and NEST, however, model all the years in between this. These are then ensured to be processed appropriately and to make sure that assumptions align and calibration is done to ensure that the right amount of people and technologies and costs are assumed in each and every scenario. In this framework, we modified the OnSSET code and adapted it to be suitable for model integration in the RE4AFAGRi framework. This is based on the GEP version 2 of OnSSET used for the global electrification platform in combination with many different actors, including the World Bank, KTH, and many others. This is often referred to as GEP OnSSET, which may be referred to this way throughout. We've tried to make as few changes as possible to the code, as this allows for any further OnSSET training or previous understanding to stay relevant for this implementation. However, some changes were necessary, and we'll explain these next. The demand modules in GEP OnSSET are overwritten, and the demand is instead taken from the EMLID process clusters. Another major change is that the milestone years in OnSSET have been changed from the typical year 2025 as a mid-year and 2030 as a final year to have 2030 instead as the mid-year and 2060 as the final year. Additionally, the electrification status detection, population growth, urbanization recalibrations, which are all typically included in OnSSET by default, are instead overwritten with the values taken from EMLID. Listing a few other key limitations here, for the code modification aspect, it's important to note that OnSSET was originally designed to run only until 2030, and 2060, our future year, is much further away than this. This causes some challenges. Firstly, OnSSET currently cannot have changing technology costs. For example, the cost of solar in the base year will be the same as the cost of solar in the future, which is perhaps unlikely to be the case. Additionally, the population density in the specific clusters can start to change as the population will grow in these clusters, but the size of the cluster will not change. Other general limitations for any kind of modeling like this is that your outputs are always completely reliant on your input data quality and accuracy. Some validation attempts of this we will show you later. It's also in OnSSET not possible to have multiple supply options combined in one settlement. For example, having standalone systems as well as the grid, or mini grids as well as standalone systems. These can change from year to year, but can't have combinations in a single year. This type of work is also very skill and time intensive to correctly learn, set up, run, interpret, and communicate these results to the relevant stakeholders. And in general, predicting the future is always inherently difficult or impossible, especially the further into the future that you go. Now we'll get into some of the critical data sets that are required to run OnSSET. These data sets are completely critical, and without them, OnSSET cannot work. Firstly, we need the population clusters, including the population counts and the area size of that area. We need the administrative boundaries of the country and sub-administrative boundaries, nighttime light intensity, existing transmission and distribution infrastructure, land cover types maps and elevation maps, solar resource, typically here modeled as the annual global horizontal irradiation, travel time to be used for determining the cost of diesel transportation, and wind speed. Furthermore, in this specific implementation of OnSSET in the RE4AFAGRi framework, other critical data sets are required. This is mostly from the MLED population clusters, which need to be processed to include all of the electricity demand for those areas from now on into the future. This includes the population counts and their future year projections, the urban-rural status and their predicted into the future, an estimation of the electricity access status of how many people in each of the clusters are expected to have electricity now, and do they have electricity at all, nightlight intensity, the size of the cluster, the administrative area name, as well as its nest allocated region to be integrated later into the nest model, and all of the demand required in this cluster. The data we require from nest is much less, however, it's still important. Here we need the average wholesale grid electricity cost over the study period. Again, we can only have one value as these numbers can't change in OnSSET. If you do not have nest or not something like it, you might be able to make an estimate of what you expect the grid electricity cost to be, perhaps from other studies or from soft linking to one of your own models. Some optional data sets that can be used in OnSSET but are not critical include the future planned transmission in the HV lines and distribution MV lines, substations and transformers, including perhaps also planned transformers, the current road network, and mini or small hydro site potential. These can sometimes make your analysis more detailed or accurate, and perhaps give you other questions or visualization options to be able to answer it. However, they are not critical to be able to run OnSSET. But here we'll get into a little more detail of how we've changed and why we've changed the electricity demand estimation in OnSSET. The original OnSSET methods are generally based on the multi-tier World Bank framework from tiers 1 to 5, and are defined separately for rural and urban populations. These are often done with everyone in a rural area getting one tier of access and everyone in the urban area getting another. However, some other approaches have been improved to try and determine these based on wealth, as well as adding demand from schools, health centers, and other productive demands. Here we've completely updated and changed this in the RE4AFAGRi project, including a much more detailed demand estimate from MLED, which estimates demand from every different energy sector. It also includes crop demand, including crop demands within the settlement and also in the surrounding settlement, and allocates these appropriately. It also has much more detailed wealth estimations with different characteristics of demand of these wealth sections, as well as projections and calibrations into the future for the different scenarios we modeled. We also here have dynamically changing energy use in these scenarios. For example, the demand of a single household may grow over time as wealth improves into the future. Next, we'll get into more of the details of how each of these different supply options are modeled in OnSSET and which data each of them requires. Here we'll go into the grid, the mini-grid, and the standalone systems as mentioned before. First up, we have grid extension, including centralized electricity generation, transmission of electricity with HV and MV lines, as well as distribution of electricity with MV and LV lines. Here in OnSSET, we take the cost of electricity generation determined from NEST, and OnSSET does not do any optimization of which types or number of power plants should be supplying the grid electricity. It only knows that the grid electricity is an option and how much it costs. It does, however, do detailed analysis of what it will cost to extend each of these different high voltage, medium voltage, and low voltage lines to electrify a community, from the high voltage transmission lines to the community, as well as the distribution lines within the community. Next, we have mini-grids, which include locally generated electricity from a multitude of different sources. OnSSET includes the options of solar, hydro, wind, and diesel, as well as hybrid combinations of these, as well as battery storage. A mini-grid also has a local distribution system to electrify the community, but does not have high voltage transmission to the main grid. Lastly, we have standalone systems. OnSSET models these as either photovoltaics, solar home systems, or as diesel generators. They are often more suitable for lower demand levels or areas that have much lower population density, as well as being far away from the grid. No transmission or distribution networks are required here, which saves costs. However, often the solar PV systems do require battery storage to be able to provide power at night. As a summary of the resources available for the non-main grid options, here we see them plotted out below. For solar, diesel, wind, and hydro, all of these available for many grids, as well as hybrid combinations of these with storage. However, for standalone systems, we only have solar and diesel available. Wind and hydro standalone systems are theoretically possible, but are much more suitable for larger communities and larger investments. Another key term that is used around the world in energy modeling, as well as in OnSSET, is LCOE, or the levelized cost of electricity. This effectively gives you one number to try and determine what the total all-in cost is required to be able to pay back a system. So all of the total costs of the system of its entire life divided by all of the energy that it produces can give you a single currency per kilowatt hour number, which can be used to compare the different options against each other to try and figure out which of all of these options is the cheapest in each scenario. We won't get into all of the mathematical details here. However, you can come back and see this or find many more resources online to understand how this works. This schematic roughly shows how each of the different technologies and the different data sources are combined together to give you the optimal electrification plan. We start at the top, inputting the M-led settlements and their demands, understanding electricity demand, and then for every different option, the levelized cost of electricity is determined to figure out which of these is the lowest cost technology option. Grids often require administrative areas, the transmission networks, and the cost of electricity to get from the grid. Mini grids have the different potentials of the different resources available, but also need to understand the distribution system costs. Standalone systems do not have distribution system costs and are often the best option for lower density customers. OnSSET does still give you each and every one of the costs calculated for these different options, even if one of these is expected to be cheaper than the other. In the RE4AFAGRi project, we've run several different scenarios and designed them to try to answer different questions. Here we'll quickly show you some of our assumptions for these different scenarios. We ran three main scenarios in this project. They are considered the baseline scenario, the improved access scenario, and the ambitious development scenario. Many more of these specifics of how these scenarios were designed and how their data is retrieved can be found in this link below. The simple version here relevant to OnSSET is more in terms of the electricity access rate targets. And in the baseline, we have assumed that the current historical rate of improvement will continue as it is, likely not to achieve universal electricity access in this scenario in any year. However, in the improved access scenario, we've decided for electricity access to halve the gap by 2030. And in the ambitious development scenario, to reach universal access by 2030, and also to ensure that 100% of this energy is provided by renewable electricity. The other scenarios in the other models do also affect the results of OnSSET, mostly with the cost of electricity from NEST changing as different scenarios require more investment or less investment, as well as the demand changing in the different scenarios, especially with more crop processing demands and irrigation demands in the different scenarios. Now we'll briefly describe how to run the model on your own computer. To do this, make sure you've already watched the software installation procedure video and have the OnSSET code, repository, replication data, and Python environments already set up and installed. Without this, the next steps will not work on your computer. To start the Python environment and Jupyter Notebook on your computer to run the OnSSET code, follow the instructions below. Pause the video if you need to be able to follow the instructions and copy-paste them. First, you'll need to navigate to the path of where you have installed the OnSSET folder of the RE4AFAGRi platform, such as this below. Your path will likely be different as mine. Then you will need to activate the RE4AFAGRi OnSSET Python environment using conda activate. Once activated, you should see the base of your Anaconda prompt to show RE4AFAGRi _OnSSET env. And then you will type the command Jupyter Notebook and press enter. This will then open the Jupyter Notebook in a browser window, which we'll show you coming up next. It's also important not to close the Anaconda prompt in the background, even while the Jupyter Notebook is open, as it's needed to operate and run the Jupyter Notebook. If you started your Jupyter Notebook correctly, it should open up in a separate browser window and look something like this. You'll see several different folders of the repository, as well as a mled extraction to OnSSET IPyNB Python notebook. We will briefly show you how to run this, but we will not be giving you a comprehensive tutorial on how to use Jupyter Notebooks or Python. Please follow this link for a free tutorial, as well as many other tutorials available online. Open up the mled extraction to OnSSET IPython notebook by clicking on it in the list. Some people sometimes get this error of a kernel not found. It's not an issue. Simply go to the drop-down menu where you see the Python 3 kernels and select the RE4AFAGRi OnSSET env kernel. When you open the mled extraction to OnSSET IPython notebook, it should look something like this. Your code, however, might look slightly different if you've got a newer version from the code repository or you've changed your scenarios. Before running your code, you might want to select specific scenarios to run, as well as maybe only selecting one scenario first to check that it's working. As this can take quite a long time to run, sometimes it's better just to run one scenario in testing than running all of them together. To run the code, go to the top of the notebook, click on Cell, and then click on Run All. This will run all of the different parts of the code in the correct order, and this will be extracting the mled results from its folder in the replication data to make it ready for OnSSET in the next step. This will not work correctly if you have not installed the extraction data correctly from the instructions in the previous video. Do note this might take quite a long time, especially if you have a slower computer or you have selected many scenarios. Next up, we'll show you what it looks like if it's completed correctly. After you've clicked Run All, scroll down to the bottom of your Jupyter Notebook page and wait for the output to look something like this. Here you will start to see a printout of some statistics in different years when it is extracting the MLED scenario code for use in OnSSET. You may have an error. Sometimes you can simply try rerunning the code or try to follow the installation instructions again more carefully. Next, when this is finished, make sure it does actually finish all of the scenarios that you have run. We'll go back to the other tab in the Jupyter Notebooks to get to the base of the repository. And then we will navigate into OnSSET, the OnSSET folder. So it will be OnSSET. It should look something like this. Inside here, we will see many different smaller Python files. These are the main OnSSET backend code, which we will not be getting to the details today. However, we will be running the IPython notebook called OnSSET scenario running.ipynb. Click on this to open it up, and it should look something like this. Again, as before, selecting your scenarios can be done by commenting out the specific code. Make sure that all of the scenarios that you try to run in the OnSSET scenario have already been correctly extracted in the previous step from MLED. To run it, do it as before by clicking on Cell and then Run All. Again, this might take quite a long time, especially on a slower computer or if you've run many scenarios. Please be patient. If you do get an error immediately, you don't have to wait and you can still try troubleshooting. But if you see that the code is running, let it run and maybe come back later. As it is running, you might see some of these outputs starting to come out below with different electrification rate targets in the different years, the different scenarios you've chosen. And then once done, it should say finished for each of the different scenarios you've run. If you scroll further down, you should see some other summary statistics output. This, for example, is the full summary that goes towards NEST for the different catchment area units and for the different technologies in the different scenarios and rural and urban numbers. Again, a different way of viewing it using the Python group by command. To see the final full results, you can either go into the Python notebook viewer or go back into your own directories and look inside the different folders. You will have an OnSSET results folder and then different folders within that. In OnSSET full results, we'll have the full output results for every single cluster that we've modeled, including all of the different details of the different years and the different technologies, as well as summary folders, including those that will go to NEST if you use NEST for further analysis. If you manage to finish the OnSSET code completely, you might want to also view some of these scenarios in QGIS. Visualizing the results in a software package like QGIS can be interesting and useful for making maps for sharing your results. We won't get into all the details of exactly how to do this. However, many tutorials and instructions exist online, as well as also those shown in the MLED course, as well as some OnSSET specific visualization links from the resources available. As the quality and accuracy of the input data into any OnSSET analysis is so important, next up we'll show you a few data validation examples of where you can go the extra mile to try to make sure that data you input is as good as possible. Here we have a data validation attempt done by us in the RE4AFAGRi project for Zambia. Here we improved and validated the population data inputs that will be used for both OnSSET and MLED. Shown in the map here, we have And shown in blue are all of the clusters from the global electrification platform based on Facebook high-resolution settlement layer data, often considered the previous state of the art, as well as Grid 3 clusters with WorldPop information that have been used for data validation in this work. Everywhere that you can see orange clusters and not blue is where the Grid 3 clusters are showing population, where the previous information does not. There are also many areas in blue where false information has been showing settlements that do not exist. This can be shown in the next slide. Here is an example of some of the information and comparison between the different scenarios. In orange, we have our clusters, also showing a much better and cleaner outline with a much more natural settlement shape, also finding many more structures and newer settlements in this area shown over here. On the left-hand side, we can see an area in a national park where the underlying Facebook data has found many settlements that are shown to be very small clusters of buildings that, in fact, when investigating, do not exist. Additionally, we've done work to try and validate and improve the grid data for both high voltage and medium voltage lines. Here we've used a combination of different sources as well as maps from utilities and visual inspection using satellite information. Everywhere that you can see the red medium voltage transmission lines from the grid finder algorithm, after the inspection and looking at the nightlight information and looking at settlements existing there, we've determined that these grids, in fact, do not exist. This can have a significant impact on the viability of grid extension in these areas, as the OnSSET will otherwise incorrectly determine that a settlement is close to an existing grid where it may not be. Next up, we'll show you how to change the scenario input assumptions if you wish to do so, or if you wish to generate your own assumptions or create assumptions for a new country analysis. To do this, you will need to go to the OnSSET replication folder that you extracted previously from the instructions and go into the OnSSET input files folder. Here you will find several different scenario specifications XR files that you will need to modify if you wish to change the scenario data. Inside the OnSSET input files folder, it should look something like this. You may have more or less scenarios depending on which version or many modifications you've made. Any modifications need to be made to each and every one of these individually to make sure that your scenarios are coherent. Opening up one, for example, there are also multiple sheets within the scenario. The most important factors here to consider are in the Scenario Parameters tab, the Specs Data tab, and the Specs Data Calib tab. Make sure to include the rural and urban target tiers as tier 6, as this will then use the custom data. 5-year target, here this does not necessarily mean 5 years, but is the variable used to determine the mid-year electrification target, as 0.74 translates to 74% electrification rate nationally. And then the final year target in this scenario is 99.8%. Also important to include the grid generation cost in dollars per kilowatt hour, as well as diesel price. Each and every sheet needs to be updated, as well as scrolling further to the right to change the other scenario variables. Here in the specs data sheet, we can also need to make sure to define the total population in the start year and end year. Also make sure not to change the start year, intermediate year, and end year values of 2020, 2030, and 2060, as this is how the code is required to work. Make sure to also update the number of people per household in the urban and rural areas if this has changed in your scenario, and to scroll further on to see further scenario information. such as here with the diesel cost and the grid costs. Here we only run a scenario that has the same cost with the high and low grid costs. Another important factor to include is to make sure to also include this data in the specs data calib sheet, as this data is also used in the scenarios. This may look like duplicating data, however, it is important to include it in all of the different sheets. How do you start an analysis for a completely new country that has not been included in the RE4AFAGRi project? Here we include a very brief overview and resources of where to go to do this. This is considered an advanced option, and make sure to reach out to us if you do get stuck, as these instructions are not comprehensive. Firstly, as this implementation of OnSSET in RE4AFAGRi is directly integrated with MLED, you will first need to follow the instructions and complete the MLED course to make sure that you have the population clusters with the correct MLED demands and calibrations for your different scenarios, as well as including the different crop processing and other agricultural characteristics. These are then used in OnSSET, but with also additional data that is added in steps 2 and 3 below. In step 2, you will need to get the required additional GIS data sets required for OnSSET. Here we have a helpful link where there's many different resources you can go to find them. You can also use your own validated data or data from private or government sources, and you can choose whether you wish to release this or keep it private. Just because OnSSET is open source does not mean that you have to publish any of your data. Lastly, once you have the data required to start, you can then either use the OnSSET QGIS plugin or the Python instruction code. These both do the same things. However, you may have a preference for one or the other. Follow this link to find the QGIS plugin, as well as information and instructions of how to install and use it, as well as the Python GIS extraction code link over here. OnSSET has already been used in the Global Electrification Platform, sponsored by the World Bank, including many others. All of Sub-Saharan Africa has been modeled in this platform and is available for free. You may wish to use this for inspiration or to understand where you can find other assumptions that might be useful for your own analysis. To access the Global Electrification Platform, go to the link electrifynow.energydata.info. Here you will find the Global Electrification Platform, which has modeled more than 58 countries. With helpful links from the Global Electrification Platform, you can also go to the page of each country and see the settlement clusters used, as well as all of the different energy modeling parameters, as well as full outputs of the results and input data. This might be helpful to find inspiration for your own modeling or to check and validate your results against those done by other institutions. If you get stuck, please reach out to us. The best way to do this is by making a GitHub issue, and this is shown in the next slides coming up. If you run into problems, try go back and follow the instructions again and see if maybe you made a mistake or a specific piece of software wasn't installed or instructed correctly. However, if you're still stuck, please go onto the GitHub repository, go to the Issues tab, and create a new issue. If you're still stuck, you can reach out to us by email, and we'll try to get back to you. Creating a GitHub issue looks like this. Give your issue a title, write a detailed and useful description of your issue, and submit it. This also makes sure that your issue, if solved, can help other people instead of everyone being helped individually.